In today's online lecture, we are going to learn about acids and bases and few basics about it. So what is acid and base? Well, generally, when we refer to acid-base definition, we are referring to the Bronsted-Lowry theory. There are few theories that give definitions of acids and bases, and all of these theories they define acids and bases differently. So Bronsted-Lowry theory is one of them. So according to this theory, acid is something that will donate a proton. Proton is a H positive ion, right? So the hydrogen atom, it contains one electron. Okay, so let's say this is a nucleus and this is one electron, and when it has lost this electron, so you're left with this nucleus. So this is known as proton, and then so acid is something that will donate a proton, the H positive ion, and base is something that will accept a proton. That means it will accept H positive ion. So if we go ahead and look here, um, towards the water. So water is something which we call it as amphoteric. Okay, we want to learn here about this term amphoteric. So what is amphoteric? The species that can act as acid as well as base. It can act as both, right? So for example, here, if I want to talk about this water, this is a water molecule. So H, two hydrogens and one oxygen. It will go ahead and accept this H positive proton, okay, H positive ion, and it will become H3O positive, right, the hydronium ion. So this water is accepting the proton, and the one who accepts the proton, we call it a base. So here your water is acting as a base. And if this is also a water molecule, right, two hydrogens and one oxygen, H2O, so it is donating a proton here. So let's say this proton is being donated, right? This one leaves here. What is left behind is OH negative. So because it is donating a proton, I can say this water molecule is acting as an acid. So water is amphoteric, you can see here. So if we react to water molecules, one of it is acting as a base, and this base is leading to this hydronium ion, which is known as conjugate acid. So this base leads to something called conjugate acid. So hydronium ion, the H3O positive, is the conjugate acid of this base. And similarly, your water, this water which is acting as acid, will give rise to this hydroxyl ion, which we will call as conjugate base, right? So this acid is leading to the conjugate base, and this is an equilibrium reaction. So you can think of many examples. The one who donate protons is called acid, for example, HCl, Hi, right? And let's move forward. There's another theory, which is called Lewis theory, and there were some drawbacks here in this theory. So according to this theory, only the acids which have proton in them, the H in them, they are only acids. But this was not true, as the things got uncovered. We also found there were some species that could act as acids, but they didn't have H in them. So this theory will cover those. Uh, Lewis theory. So basically, what are Lewis acids? According to this theory, acid is something that will accept electron. Okay, so it is not necessary that it should donate proton. It should have a proton to donate, right? So this Lewis acid is different from the Bronsted-Lowry theory acid, right? So the condition here is that it should just accept electron. So for example, BCl3 here, I will go ahead and draw it here for you. So if you see here BCl3, okay, so these are the three chlorine molecules. So this boron will be essentially bearing a partial positive charge. Chlorine are very electronegative. So this partial positive charge is ready to accept an electron if there is some electron pair in its vicinity, right? So this can act as a Lewis acid, right? What is a Lewis base? So it will donate electron. So Lewis base is something that can donate electron, right? And if you see it will accept a proton. So they are same Lewis bases and Bronsted-Lowry bases. So if you take this example of NH3 here, I'll go ahead and draw it here for you. NH3 looks something like this. So there are three hydrogen, right, and one lone pair here. So it can donate electron pair, right? So it is a Lewis base, and also it can accept the proton also. So this lone pair, if there is H positive ion in the vicinity, it can go ahead and attract it towards itself, forming NH4 positive, right? This is a ammonium ion, right? And this is a base, right? So this NH, this one is Bronsted Lowry base as well, right? So the differences between the acids, the bases are like similar. Now moving on, the terms we want to learn next are protic and then aprotic. So protic means that contains protons. Protic, the proton word, it comes from hydrogen atoms. And aprotic, does not contain hydrogen atom, right? Not containing H atoms. So next we want to see here is this thing. Amphoteric we already did. It can act as acid as well as base. Okay, water reaction I already showed you. So how this water molecule over here, this base is leading to its conjugate acid, which is written as Ca here, and this acid is leading to conjugate base, right? Because this reaction is in equilibrium. Okay, this reaction is in equilibrium. What we want to learn here is this thing, because we do know from our previous knowledge, equilibrium expressions, in equilibrium reactions, we can write equilibrium constants. Generally, we write it with K, okay? Since these are the water molecules, okay, which are reacting here, so the equilibrium expression is written as Kw, okay? So if we recall, how do we write the equilibrium constant? So it is a multiplication of concentration of products. So what are the products here? Hydronium ion. So the concentration of hydronium ion and the concentration of OH negative ions, right? So the multiplication of concentration of the products on the top, and what will be in the denominator? The reactants, right? So this water, okay, liquid, and this water, liquid. But we do want to know that in the equilibrium expressions, when doing this calculation, what we don't count is liquids as well as solids. Okay, so let me just clear it up. So we don't write liquids and solids. Let me just give me a quick second. I will erase this one because I don't want to refer to this expression here. Um, so solids and liquids are not allowed in the expression. So because if you see here, this water is liquid, this water is liquid, so we can get rid of these. So I'll go ahead and erase these from the expression. And what we are left here is with the aqueous ions here. So these is the aqueous ion, this is the aqueous ion. So what are included is gases and aqueous. Okay. So aqueous ions, gases, they are included. So what we're left with is this expression Kw, which I have written here. Kw is equal to hydronium ion concentration times OH ion concentration. And what we want to know here is this thing. So the Kw value, it has been calculated at room temperature. And what is the value of that? It is 1 into 10 to the power negative 40. This is the value of Kw. And if we look here, let's say we have a solution here, okay? We have the hydronium ion hydronium ions here and hydroxyl ion here. So if we look into this hydronium ions, if the concentration of hydronium ion increases 10 to the power negative 7, okay? If it increases 10 to the power negative 7, then we call that solution as acidic solution, okay? What do we call it? We call it acidic solution, okay? So if it is, the concentration is greater than 10 to the power negative 7. However, if the hydronium ion concentration is less than 10 to the power minus 7, so that means these are less and hydroxyl ions are more. Okay, it should be essentially less than 10 to the power minus 7 to be referred to as a basic solution, right? And next, what we want to learn here is this: if your hydronium ion concentration is equal to 10 to the power minus 7, okay, then we call that solution as neutral solution. In neutral solution, hydronium ion concentration is equal to hydroxyl ion concentration, okay? And the next thing we want to learn here is if you go ahead and increase the temperature of water, so what will be the impact on Kw? It will also increase. So the value of Kw will increase, okay? Now, let's go ahead and learn about strong acids, okay? So we were discussing about acids as well as bases, and if we talk about acids, so acids can be of two categories, okay? Essentially there are three. So moderately, I will tell you strong acid, and weak acid. For now, we want to concentrate here, and there is a third category of moderate acids. We will go into those step by step. So let's look into strong acids first. So for example, this is a general acid HA. This A can be anything, ClFibr. Okay. So let's say this is a very strong acid. Okay. So this will be going, the reaction will be going like this. It will dissociate into H positive and E negative ion. Okay, so if you have HA in the solution, you will find it as H positive ions and E negative ions. So what we find is that because this is the acid and this will be the conjugate base. Okay, this A negative is the conjugate base of this acid. So for a strong acid, the conjugate base is very stable. Okay, and it is easily formed because this is very strong. It will be very reactive. It will immediately dissociate into this, okay, H positive and A negative. So this conjugate base is very easily formed, and in nature if something is easily formed, that is very stable. So that means because this is equilibrium reaction, so this A negative will not be very desperate to go ahead and react again with this H positive to form HA. So the percentage or the equilibrium will lie more towards the right. Okay, so the forward reaction is more favored as compared to the backward reaction. So this is what we are saying, and we call this as a weak base because it is not very reactive. It is very silent. It is very calm. It is stable. So it is a weak base. Okay. So strong acid will generate a weak base, weak conjugate base, okay, and it will be because its stability is very high. So it will not be because if you are very stable, you won't like to change your position, right? So it will not be very desperate to go ahead and move again and form HA, okay. Now, next thing what we want to learn here is that for conjugate acids which are weak, okay, let's talk about the weak acids. So what will happen? So if you go ahead and mix, let's say you have the salt of this HA, this weak acid, and then you let it dissolve in the solution. So a very few H positive ions will be there and A negative ions will be there. So for example, what we mean by this is this HA, let's say you start with 100 grams of this. So only 20% of this, that means only 20 grams will be dissociating, will be ionizing in the solution, and 80 will remain intact. Okay, this HA 80 you will find, so more of this you will find the intact form as compared to the dissociated form. So for weak acids, this is always true. Okay, they will not ionize much. Only few percent will be ionizing. So if we go into details of the conjugate base here of this weak acid, it will be unstable. Okay, it will be hard to form, and it will be a strong base. Okay, so for weak acid, the weak acids they generate conjugate base which are very unstable. They are hardly formed, and they will be strong bases because this is a strong base. So wherever the thing has ionized, it will be very desperate to combine with Ha because it is very strong. It will be immediately, if it is formed also, it will go ahead and immediately combine with H to form Ha again. Okay, the weak acid. Okay, so the equilibrium will lie more towards the left, more towards this side as compared to the this side, the forward. So the reverse reaction is more favorable in this case. Now, next thing what we want to learn about is about the strength of acid. Now, we were saying it is strong acid, it is weak acid. So, how do we decide that? So, the strength of acidity of acid is directly proportional to the stability of the conjugate base. So, who decides the conjugate base? If the conjugate base is very stable, like here, then your acid strength is very high. If the conjugate base is unstable, then your acid strength is weak. Okay, so strength of the acid directly depends upon the stability of the conjugate base. Now, how do we decide whether your conjugate base is stable or not stable? So, larger the conjugate base, so this is one parameter. Larger the conjugate base, more will be it's stable. Okay, so just for the example purposes, let's say there is a fat person, there is this tiny person, a thin person. So this thin person will be very active as compared to this fat person. Okay, he'll like to sit more and not move around much. So similarly, if you look into the examples of the halogens here, so I have these acids here, HF, HCl, HBr, and HI. So what is varying here? The halogen is varying here. And as you're moving down, fluorine, chlorine, bromine, and iodine, the size is varying. So the size is increasing downward. So what do you think of these four? Who is the strongest acid here, HF or HI? So we just talked that larger the conjugate base. So the conjugate base here will be iodide ion, Br negative, Cl negative, and fluoride ion. So who do you think will be more stable and who will be more unstable? So iodide ion looks like this. It's bigger in size, and fluoride ion looks like this. So we just talked, if it is larger, then it will be more stable. It will stay calm. It will not go ahead, move randomly, and react. So this will be more stable, and the more stable gives you a strong acid. So that means this is a more stable conjugate base, and this will be a very strong acid, right? So this is how your acidity trends look like for these acids. So acidity increases in this way. HI is the most strongest acid as compared to HF. Now, moving on, we have some other examples. Let's go ahead and talk about the categorization of acidity on the basis of electronegativity. Okay, so for example, I have these three acids here: CH4, NH3, and water. Okay, so what would be the acidity trends, in which way it will be increasing and in which way it will be decreasing? So, as we do know from the definition, so acidity we define, it can give away easily proton, right? So if we go ahead and talk about water, so this is how your water look like. So water is like this, okay? So oxygen is very, very electronegative. So this is a there is a polarization difference here. So this will be partially negative. This will be partial positive. I'm sorry, like electronegativity difference here. A lot of differences here. So this bond is polarized. So this is a partial negative side, and this is partial positive side. So this H is very, very positive, so it will be easily donated, right? He has more authority, and he will be actually very eager to kick out this hydrogen from here. So this can happen. This can readily happen, right? So that means it is quite acidic. Now, if we go ahead and talk about CH4 here, so how does CH4 looks like? So this is the thing. There is not much electronegativity difference between carbon and hydrogen. So there is no such thing as partial positive and negative thing. So this cannot happen on its own, right? So this carbon is not much willing to lose its hydrogen from here. Okay, so this is not acidic. Okay, and if we talk about this NH3 here, so NH3 I already told you, it looks like this. Okay, so nitrogen and hydrogen bond, if you look here, is also very, very large electronegativity difference. However, it is smaller than this oxygen and hydrogen. Oxygen is way more electronegative than nitrogen. So this hydrogen will be also ready to, leave here. It is ready to be donated here. So, but not as compared to, water. So this is how the acidity trends look like. So in this way, this acidity increases, right? Now, this is about electronegativity things. Now, let's talk about uh, something else. Let's go ahead and compare your COOH acids and water. So, what do you think? Let's say I put CH3 group here. So, what do you think? This is a strong acid or this is a strong acid? So, who decides? So, we already told you the conjugate base is the parameter that decides the strength of the acid. So, the stable, the conjugate base, so more will be the strong strength of the acid. So water, you already know, it dissociates like H positive and OH negative. If you go ahead and see here, CH3COOH, this molecule looks like this. And if it donates H, so if it donates the H positive, so what will be left? What is the conjugate base? How does it look like? It looks like this. CH3C double bond O negative. Okay, since this H positive is lost from here, this this electron pair lies to oxygen, lies with oxygen, so this is the negative charge. So what will happen here? So this conjugate base can undergo resonance. So this negative charge can move here, and this pi bond will be pushed onto the oxygen. So what will happen? Resonance is happening here. So I have resonance, the second resonance structure here. So when this moved, I have the double bond here. and this is pushed and I have the negative charge here. So this is a resonance stabilized conjugate base which I'm having. So as we do know from our previous knowledge, if something is giving us resonance, so extraordinarily stability is associated with that thing. Okay, it becomes extraordinarily stable if it can undergo resonance. So this is same thing. So that's why this is a stronger acid as compared to water. Now let's move forward and let's look into some more terms. Monoprotic. Mono means single. Protic means this word is from proton. So mono means single proton. So that means acids that those contain only single H. For example, HCl, HF, HI. We have talked about many. Poly means many, protic means proton. So poly means many protons. Polyprotic means many protons. So it has more than one proton. For example, if I talk about H3PO4, this is also acid. Okay, and so this is how it looks like H3PO4. Okay, so P is the central. Okay, double bond O, and then I have three OH bonds here, right? So this is polyprotic acid. It comes under that category. Now let's go ahead and talk about the acid-base equilibrium again. And let's talk about the strong acid. So let's say we have a strong acid, it reacts with strong base. So because you already know the strong acid will give you a weak conjugate base. Okay, so I will have a weak conjugate base. And the same thing is true for the bases also. If you have strong base, its conjugate acid will be weak. Okay, the same thing holds. So the conjugate acid will be weak, it will be stable, right? Things like that. So strong base will also lead to weak conjugate acid. So this is how this equilibrium reaction looks like between strong acid and strong base. Now, strength of the acid, how do we decide what's the number if we have to look into the calculation? So pK is the measure to do that. So pKa, if it is less, then it is more acidic. So it is the vice versa. It is the reciprocal relationship. So the pKa value, so smaller it is, more acidic it is in the nature. So larger it is, the acidity will be less. Okay. Now, if you go ahead and check the next thing, we will talk about acids and bases here. So for example, I have this Ha plus water giving hydronium ion and A negative ion, right? So this Ha, what it is doing, this Ha is becoming A negative over here, right? So that means this is donating Ha. It is getting rid of this H, okay? So the thing that get rid of the proton, it donates the proton, that is the acid. So I will say this is acid. So if this is acid, then this is base, right? So that H is accepted by this water and it is becoming hydronium ion here, right? That H positive is accepted by this water and it is converting into H3O positive. So I can write here, this base is leading to this conjugate acid and this acid is leading to conjugate base over here. Now, what we want to do next is this thing. If your hydronium ion concentration is more, okay, if these hydronium ion concentration is very, very high, like that means a lot of H positive is being, released or it is donated from this H, then the acidity of the solution will be more. So how do we measure it mathematically? So pH is the answer to that. Okay, since you saw Kw was equal to 1 to 10 to the power negative 14, so so concentrations are like that. Okay, so we don't want to deal with these numbers 10 to the power minus 14, this and that. So what we do, we just go ahead and put negative log in front of these numbers. Okay, negative log of 10 to the power minus 14 will give you 14 as the answer, right? So Kw, so negative log of Kw will be 14. So this is the same thing we are doing here. So pH is negative log of hydronium ion concentration. Okay, so whatever the concentration is 10 to the power negative, so you took negative log of that. So let's say for the neutral solution, you already know the hydronium ion concentration is 10 to the power minus 7. So if you go ahead and take the negative log of that, you will get 7 as your answer, and it's better to deal with these numbers as compared to this. So we call this thing as pH. So this is the pH. pH is what's the formula, negative log of hydronium ion concentration. And similarly, what is next here? Similarly, you can go ahead and talk about the bases also. So this base, is reacting with water. So what this base is becoming here? Base is accepting the proton. B is converting to BH positive here, right? So what is happening here? This is accepting the proton. So whatever accepts a proton, we call it as base. And this hydro water here, it is losing the H and it is becoming OH negative. So that means I can say this is acid, right? It is losing H positive. It is donating, right? So this base is becoming BH positive. This base will give you conjugate acid and this acid will give you conjugate base, right? Now what next we want to see here, similarly as we said, if OH negative concentration is more, then basicity will be more, that solution will be addressed as basic in nature. And if you want to see the if you want to calculate the concentration of OH negative ions and then you put negative log in front, right? So you should be able to get the pOH of the solution, right? And what other formula? So this is one formula. This is the second formula you want to pay attention. This formula we already did in the previous slide. Kw is equal to concentration of H3O positive times OH negative, and Kw at room temperature is 1 into 10 to the power minus 14. So this is the third formula I will write here. And the fourth formula, if you go ahead and add these pH plus pOH, okay, then it will give you 40. Okay, so the derivation of this formula is very simple. So you can just take log on both sides. Then this number will come out to be 14. So pH plus pOH will be equal to 14. Now these are four formulas here. Let's go ahead and do some practice problems here. So this is these are the couple of questions here. Let's see. So the first question is identify the acid base Ca and Cd. Like I was doing it there, I was writing acid and base, and then I was writing conjugate acid and conjugate base. So you could be asked this type of question on the exam. So what you can do is, for example, NH3 plus water is giving you NH4 positive and OH negative. So identify. I've already written the answers. Maybe let me just go ahead and uh, struck them out so that you can practice those. Okay, so what is happening here? NH3 is becoming NH4 positive, right? So it is essentially accepting a proton. So something who is accepting a proton is the base, and this water is converting to OH negative. It is releasing the H positive, it is donating. So this is acid. So base converts always into conjugate acid, and this acid always converts into conjugate base. So base essentially have negative and these acids they have positive. Okay, now what about the next one, H2CO3? You can go ahead and like look into these problems. This is a similar kind of problem. So H2CO3 is reacting with OH negative. It is becoming HCO3 negative in water. So if you go ahead and check here, what is happening to H2CO3? It is becoming HCO3 negative. It is donating the proton. So something that proton, it is donating the proton, we call it acid, and this acid will be converting into conjugate base. And this OH negative, what is happening to this OH negative? It is becoming water. It is accepting that proton. So because this is accepting a proton over here, we will call it a base, and this base is converting into conjugate acid. Similarly, you have the C problem. Similarly, you have the D problem. You can go ahead and look into these. Let's move on to the question number 2. NaOH solution has hydroxyl ion concentration 3.5 into 10 to the power negative 3 molar. Now, what is the pOH? What is its pH? So, what will we do for this type of question? So, what is given here? OH ion concentration is given, right? Which is 3.5 into 10 to the power minus 3. So, with this piece of information, I can go ahead and calculate pOH. pOH is negative log of OH negative ions, right? So, what is the negative log of 3.5 into 10 to the power minus 3? It is 2.46, right? So, pOH comes out to be, I will go ahead and write here, pOH is equal to 2.46, right? And then what is asked? I am not being asked pH. Sorry, pOH. I am asked pH. So which formula I will do? I will use to find pH. So I do know that pH plus pOH, the last formula which we did, is equal to 14. I do know pOH. It is 2.46 is equal to 14. How do I come to know about pH? I will go ahead and subtract it from 14. I will get the pH value. It is 11.5, right? Similarly, you have some more practice problems on pH. So this is a pretty simple one here. The third one, pOH is given 4.5. find pH. So you will go ahead and subtract it from 14. Similarly, pOH is given. What is the hydroxyl ion concentration? You can do that, and similarly, you have another problem here. So this is it for this online lecture. I will see you next time. Thank you.